Yesterday, we talked about G, Gibbs free energy, and 4 different ways to calculate. We reviewed Gibbs-Helmholtz equation, which relies on enthalpy and entropy. Then we looked at an overall products minus reactants summation using tabular data or pairing tabular data to find H and S to find G. So you could have also paired this process within the original Gibbs-Helmholtz. And then I introduced Gibbs-Helmholtz, a G equation that connects for a reversible reaction, K and Q. K being, of course, the ratio of products and reactants at equilibrium, and Q being the ratio of products and reactants not at equilibrium. And for the most part, everything I taught you yesterday is basically find the equation on the equation sheet, plug in what you know, solve for what you don't know. It's a basic plug and chug. So for this problem, all you had to do was you had to solve for K. So what you got was you should have put in 1, change your degrees to Kelvin, okay? Then you got to change your G, well, you get your G. So it's G equals 26.5, oof. Okay, 26.5 kilojoules per mole. And honestly, yeah, per mole, which is equal to, you would use the K equation, so negative RT ln Q, negative 8.314. This is in joules, so you'd actually want to convert this to kilojoules to make it match. So 0.008314, okay, joules per mole Kelvin, okay, times 2, I don't know what 227 is plus 298, but whatever that is, times your temperature in Kelvin, and then times ln of K. And you would have solved for K, and you would have gotten that K equals 0.00171. So for this reaction, this is reversible reaction, which direction is the favored direction? Based on the K value that you found. Which direction is actually favored if you have a less than 1 K value? Yeah, the reverse direction is favored, which is why the G being positive tells us that the forward is unfavorable, non-spontaneous. G being positive means it's unfavorable, non-spontaneous in the forward direction. The G for an equilibrium-based problem is always assuming G of the forward, okay? So, okay. Next one. Now you have this unique equation, and all these are on the equation sheet. All of these are provided where you have Q not at equilibrium. And this one's a little different because you have to account for that you're at an instantaneous moment in the reaction process. So that's why this isn't a direct translation of the other equilibrium. It's not like just negative RT ln Q. It's different. We have to account for the fact that you have to hold it against the standard. Okay. Yes.
Why is your R so tiny?
Because it's in, kilojoules. I converted it to kilojoules, and otherwise it's in joules. 8.341 joules versus this is 8.34314 kilojoules.
Okay.
Yeah. Okay, so this next one is again a plug and chug. So all you would do here is you were given the partial pressures of these 2 species. You would find that Q is equal to the partial pressure of N2O4 product all over partial pressure of NO2 raised to the stoichiometric coefficient of 2, which would give you a Q of 20. Then you would turn temperature into Kelvin, and you would get 298.15 because you're told it's at room temp or 25 degrees Celsius. And then you would use R, and of course you want to be careful of the units. So what you would do is you'd plug in that G, and notice this is not under standard state conditions, okay? This is not a G this is regular G because you're not at equilibrium. You're under abnormal, quote unquote, unstandardized conditions. And you were told that the standard G is negative 5.39. So you would just plug in negative 5.39 kilojoules, okay? Because we're using the equation G equals G standard state plus RT ln Q. You just plug in what you know. Plus 8.314 joules. Thank you. Okay, I'll pay you later. Okay, times temperature, which is 298, times Q, which is 20. And of course, when you're doing this, keep in mind that your units are different for this part. So just keep that in mind when you add them together, that you have different units. So you would eventually convert. And then you would get that G for under non-standard state conditions, not at equilibrium, is equal to positive 2.0 kilojoules per mole. And that would mean that your reverse is more favorable. That wherever you're currently in your product, or sorry, in your reaction, you're going to actually see a shift backwards. Wherever you're currently at in your reaction, you're going to see a shift backwards to reach equilibrium. So a lot of it's just kind of pairing what you already know, to be honest. Nothing crazy new. It's just plugging it into different equations. Okay, so you guys should feel pretty good about plug and chug at this point. You could do the next practice problem. If you did it, you would find that the answer is that G is equal to 1.3 kilojoules per mole. You could figure that out on your own. So again, we see that this is in the reverse direction is more favorable. Okay, so that's where we ended off yesterday. Now today, I'm going to talk to you about electrochemistry. How we take this concept of G and we start applying it to redox reactions in actual lab, in industry, building batteries, building voltage system, building circuits, stuff like that. So I put up electrochemistry review. Honestly, the biggest review was reminding you guys how to assign oxidation states. I have full confidence that you can figure this out on your own at home, okay? You'll figure it out in time. I know you will because you have to. Okay. And then of course I did a quick reminder about half reactions, how we track electronically speaking, how many electrons are being transferred, reduction direction versus oxidation. And then of course you want to balance it so that whatever you lose in the oxidation, you gain in the reduction half so that your completed overall redox reaction is electronically balanced and accounted for. Okay. Now I'm going to get into, okay, how does this idea of reduction potential and redox reactions help us understand batteries, voltage, and eventually the G concept? So we have a table where we actually quantify the electron or electrochemical potential or the likelihood of electrons flowing in a reduction pattern for a certain process known as the standard reduction potential table. And what this does is we can predict using this table which chemical species will be the most easily oxidized and the most easily reduced. Who would be the partner? Who would serve in a reaction in a battery? Who would serve as the one getting the electrons? Who would serve as the one losing at the electrons? How would we piece together the battery? Okay. So what you see here is you see that as you go up this side of the table, this is more likely to be reduced when you go this direction upwards. When you go the other direction, this is more likely to be oxidized. So obviously, if you flip the reaction, you can see why it has opposite categories on the table. So like F2 going to 2F minus is a highly reduced reaction. It's really likely going to serve only as reduction. F is only going to gain electrons. But if I were to flip it and say, what would be the likelihood of 2F minus going to F2? It's like barely likely. The oxidation process for that is highly unfavorable. A strong reduction process is a low oxidation process for the same two species, for the same like kind of species pair. Okay. It's not quite conjugate, but you could kind of think of it like that, right? So what we do then is what we say is that the left column, on the left column, it's elements that will take electrons spontaneously. Okay. From species below and to the right. So the higher up, the more likely to be reduced, like what I said. And what I mean by it's an element that will take spontaneously from the species below and to the right, that means if I were to be lead 2 plus, oops, hold on, lead 2 plus, lead 2 plus is going to spontaneously take from chromium solid. It's spontaneously going to be reduced by chromium, and chromium itself is going to be oxidized. If I were to partner lead and chromium, lead 2 plus and chromium solid, lead 2 plus would undergo reduction. Chromium solid going this direction, the oxidation direction, would be oxidized, and that would be totally according to the universe's preferences. Okay? It'd be spontaneous. It would just happen, that natural flow of electrons in that direction between those two species. Okay, and then you see here another example. Right column rise, right column. I have a really hard time with my R's. I went to speech therapy twice as a kid for it. Okay, elements, these are elements that will give electrons spontaneously. Two species above and to the right. Oh, sorry, and to the left. I get my right and left mixed up, guys. Above and to the left. Okay, so the lower down on the left, what is this, my right column? The lower down on the right column, okay, the more likely you are to be oxidized. So reduction potential then quantifies. It's a value that quantifies, okay, how likely a chemical is to be reduced. So we always write reduction potential in the perspective of reduction. So if you have a really low reduction potential, that means you're probably a better oxidation. You're probably a better oxidation, which means you're probably pretty low on the right side of the column. You're better going this direction, losing electrons than you are gaining. So you have a low reduction potential. You have a low possibility of being reduced. Okay. So higher on the left column, you have higher reduction potential value. Lower on the right column, you have a really low reduction potential. You're not likely to be reduced at all. We measure reduction potential in the units of volts because it connects directly with the electrical flow of electrons. Crazy, okay? So when we look at these, what we often do on the AP, they often ask you to pair up two reactions, and they give them to you in the form of both reductions. And you have to decide who actually is going to be reduced and who's going to take on the oxidation role based on the reduction potential value. So what we want to see is determine whether a spontaneous redox will occur. So what we have here is we have an A, iron 3 plus. And what we see is that iron 3 plus is located on this table right here. Then we have it partnered with chlorine minus. And chlorine minus is located on this table. Chlorine minus is located on this table up here. So what we have is we have chlorine minus is preferred to be oxidized, and iron is preferred to be reduced. But here's the problem. The chlorine is higher than the iron. The oxidation is higher in the table than the reduction. So what we would say is that Yes, iron would be reduced and chlorine would be oxidized, but this is not a spontaneous process. I'd have to force it to happen, would have to be forced. Because what we say is, in order for a spontaneous reaction to occur, your oxidized species has to be below your reduction species. You can kind of think about it as the oxidation species lets go of its electrons and the electrons float up to the reduction species. That's more natural. Think about your electrons in a balloon because they're very voluminous. They have basically negligible mass, but they're all volume. They float up to your reduction species. That's a natural process that's spontaneous. But if you have to take your electrons from your oxidation species that's above and push them down to your reduction species to accept it, that requires an outside driving force. That's not spontaneous for super voluminous, airy electrons, going with the analogy. Okay, so it could happen, but you'd have to force it. So A is not spontaneous. Calcium and zinc. Calcium neutral and zinc 2 plus. Okay, calcium would undergo oxidation if we look here. Calcium you can find here, and zinc 2 plus you can find here. And we would see that calcium definitely is the oxidation species and zinc is definitely the reduction species. But the question is this spontaneous? And it is yes, because our reduction species is above our oxidation species. So we would say calcium is oxidized, zinc 2 plus is reduced, and this is definitely spontaneous. The universe would just naturally have it flow like this. Okay, C. What you're looking for with C is I minus in aluminum. So if you look at the table, I minus is, well, here's aluminum and here is I minus. They're both oxidations. So is this a redox? No, because according to this particular state that we're looking at of the species, we say no because each species would undergo oxidation. Okay, so I'm gonna have you do the practice problem for warm up tomorrow because I just want to continue going through. So what about with the single replacement reaction? How do we know when we are going to get a spontaneous redox single replacement reaction? And by the way, every single replacement reaction with a metal is a redox. Same with the chlorine. It's always a redox. So what we say is for this problem, we have a reaction between chlorine and pure chlorine and sodium bromide. And the question is, will it spontaneously produce pure bromine and sodium chloride? Will we see that Cl2, when it reacts with NaBr, and it goes to Br2 and 2NaCl, will this happen naturally? So the net reaction for this, by the way, is going to be Cl2, 2Br minus, Br2 minus, diatomic, and 2Cl minus. That's the net reaction because sodium doesn't change oxidation state. So it ends up being like a spectator element in this case. So then we say based off of the net reaction, okay, do I see, what do I see? Well, I see according to this reaction that chlorine would be reduced. It would go from 0 to -1 oxidation state. And bromine is oxidized in this case. It goes from a -1 to a 0. So the question is, does this actually occur naturally? So I look for chlorine 2 and bromine minus. I look for that in my table. So chlorine 2 and bromine minus. Chlorine, here's bromine minus. Chlorine 2 is right here. Okay, so chlorine 2 is above my bromine minus, which means in order for it to be spontaneous, chlorine 2 would have to be reduced. And it is. Chlorine 2 serves the role of reduction and it's above my bromine, which is serving the role of oxidation in this equation. So I say, yes, this is spontaneous. Okay. to be spontaneous. Absolutely. And we'll do this as a warm up because I think I have 5 minutes left. So then we look at, okay, what if we have a mixture of several ions that could do redox reactions with one another? What would be the most likely combination, Sophie, to occur? So what we say is that it occurs between the species that are the strongest oxidizers and reducers, kind of like acids. It's the strongest pair that works, that we say is the predominant one. So what we would do is we'd be given a bunch of ions, chlorine 2, Ag plus, SN2 plus, and I minus. And we would find that if you look at the table, okay, the form of these species that is preferred to be reduced is Cl2, Ag plus, and SN2 plus. We would also notice in the table that the form of these species that can be oxidized is I minus, can be oxidized, and SN2 plus can also be oxidized. It can be reduced and oxidized relatively favorably. There are 2 reactions where we see SN2 plus on the reduction side and SN2 plus on the oxidation side. And so then we would look at is who's a better reduction, Cl2, Ag plus, or SN2 plus? So we would say then that Cl2 is here, Ag plus is here, and SN2 plus is here. On the reduction side, Cl2 plus is higher, more likely to be reduced. So this would be our predominant reduction. Now we got to figure out who's the better oxidizer. I'm looking for I minus and SN2 plus on the right side now, the oxidation side. So I look for I minus, and I'll change to orange. I minus is right here. Oops, I'll do it like this. And SN2 plus is down here. Okay, so who's the better oxidizer? It's the opposite now. Who's lower on the table? SN2 plus. So we would say that the redox would occur between these two. These 2 species would undergo redox together. That would be the spontaneous predominant reaction. Okay, so what we would get then for half reaction is that Cl2 gains 2 electrons and becomes 2Cl minus for half reaction. And SN2 plus loses 2 electrons and becomes SN4 plus. And so my net reaction would be that Cl2 reacts with SN2 plus to produce 2Cl minus and SN4 plus. And that is how you use reduction potential. And that is the end of our lecture.